This week as our speaker, Evita Nestoridi from Princeton. She did her PhD with Peres and Diaconis, and now she's at Princeton, and she's going to be talking about joint work with Allan Sly.
Thank you so much, Jonathan. Thank you so much for having me. Let me share my screen and get started. I guess, let me. Okay, I'm just writing the title, which is Mixing Times for the Upper Triangular Walk over the integers mod m. And as Jonathan said, this is joint work with Allan Sly. Okay,
You're muted, Evita.
I'm not sure how this happened. Usually my son presses the mute button, but he's not here to be blamed. So hopefully you can hear me now. So as I said, I'm going to be talking about mixing times for the upper triangular walk with entries over integers mod m, and everything is going to be joint work with Allan Sly. So I will cut to the chase, and I'll tell you what the problem is, and afterwards I will tell you how it came to be and why this is interesting. So we will consider, okay, yes, the group of n by n matrices that are upper triangular. So they have zeros below the diagonal, ones in the diagonal, and all other entries are over mod m. Okay, and the random walk that we will be studying, let me write that these are n by n matrices, by the way, so that it is clear that we have two parameters, that is n and m. And the random walk, first of all, in discrete time, suggests to pick a row uniformly at random. The rows that I'm having in mind here are between 2 and n, so we cannot pick the first row. And then we flip a fair coin. And if heads, so if heads, we add this row to the row above. If tails, we subtract it from the row above. And that's why we don't include row 1 in our selection. Okay, and just to avoid parity issues, we can say that we have laziness as well. So with probability 1/2, we do nothing, and with probability 1/2, we do what I described. And I do want to write the continuous time version. I'm going to be using both. You know, wherever it's more convenient, I'll be saying things discrete time. Whenever it's more convenient, I'll be saying things continuous time. And likely the mixing time, we're going to see later, of the two that they're comparable, the mixing times. In continuous time, what we do is that we assign rate 1 Poisson clocks to these rows. So assign independent rate 1 Poisson clocks to rows 2 to n. And then when clock I rings, then we do exactly what I said. So we repeat this, let's call it star, then we do star. So we flip a fair coin. If heads, we add the row to the row above. If tails, we subtract it. I could have said that we have Poisson 1/2 clocks. And then we add and subtract. Anyway, the question is, okay, how long until we end up with a random element of the group? And I will make everything rigorous, of course. How long until? So how many times do we need to repeat this in the discrete case, or what should the time be, continuous time, until we get uniform element of GNM? And of course, I mean a roughly and approximately uniform element of the group. Okay, so I'll set up the notation now. Of course, people who are familiar with mixing times, might find it a bit boring, but I think it's necessary. So first of all, we're going to build up the following matrix. If A and B are elements of the group, so they're matrices, PAB is just the probability of moving from A to B after one step. Okay, we notice that P is a matrix. The number of rows and the number of columns is the size of the group, and it is symmetric. This is important because later on I will be talking about eigenvalues, and so the fact that we are symmetric makes us feel better. We have real eigenvalues. Okay, now if we take the tth power of this matrix and we look at the AB entry, again we get the probability of moving from A to B, but now in t steps. Okay, and just in case you hear me say this P is the transition matrix. That's the term, transition matrix. Okay, now standard theory. So if we denote this by PAT of B, we notice that as B varies, this gives a probability measure, and as t goes to infinity, this converges to 1 over the size of the group, so the uniform measure on the group. And so this is as t goes to infinity. And we want to study this convergence, and usually we study it with respect to the total variation distance, which is just 1/2 of the L1 norm. And we actually look at worst case scenarios usually. So we maximize over the starting state. And I am going to denote this as D and T. It is important for later to remember this notation. So I will remind you then, but D and T is basically the total variation distance when we maximize over starting points. And then the mixing time, because you're going to hear me say this a lot as well. And this is basically the main question. If you give me an epsilon, I should be able to tell you how big T needs to be for D and T to be small. Okay, so if we give me an epsilon, we're going to take infimum of T so that D and T is less than epsilon. And that's why I wanted actually to set up things in discrete time, because this is very nicely explained in discrete time, and the results will be stated in discrete time just to be consistent with the bibliography, but the proof will be continuous time. One last thing about notation, and in case I don't want to forget to say it. So xt or xt will denote the matrix that we get at time t. Say that now we start at the identity because we're in a group starting at the identity. We're in a group, it doesn't matter where we start. These two notations will be the matrix at time t. Sometimes I confuse putting it up or down. And then xti will be the ith row of the matrix. Okay, hopefully I will explain it again when the time comes, but I don't want to forget the notation. Okay, so now I'm going to write our first theorems. Now that we have all the setup. Actually, maybe it's a good point to ask, do we have any questions? And I'm not looking at the chat, so maybe I should.
There is a comment from Jonathan.
Okay, it's a comment from Jonathan. Okay, yes. But feel free to ask any questions if you want, in particular concerning the first theorems that I'm going to write right now. So theorem 1, for general N and M. And again, these are all joined with Allan Sly. There are universal constants. There are positive A, B, C, D constants, universal on N and M, such that.
Your writing is not showing.
There we go. Yes, and I had to change that. Okay, so luckily I hadn't said anything interesting other than we have 4 constants that are universal on N and M. And the mixing time, T and M, will be one of these constants times M squared and log N plus. And this is a discrete time. Let me say this. So M squared N log N plus N squared E to the C log M to the 1/2. Sorry, no, this is the next second theorem, to the 2/3. Plus the window that we get, which is N squared, M squared and log N. So if we take this time, then the total variation distance is small. And here C is a constant bigger than 1, so it contributes in the window. Okay, so this is our first theorem, which works for any N and any M. I'm going to write the second theorem as well, and then we can discuss them a little bit. So we get better estimates, again, discrete time, if M is prime. So let me write it down. We can write T and M to be D times M squared.
Sorry, but just in the first theorem, so the C inside the exponent and the C in the second additive term is the same C? Or?
No, let's change it. One is capital, one is small, but it won't be visible. So let's change this C into a capital K. So we're better. Okay? A good point. In the paper, we are using so many letters that at some point we had to introduce capital and small. But here we don't have to do this. We're not going to get into all the technical details. Okay, for the prime case now, we have a sharper answer. And we don't need the K anymore because we can plug in 9. And this log M to the 2/3 becomes a square root. But the window is the same. Log N. So I'm not going to write the rest of the theorem because it's identical, but basically this is what changes, T and M, and this is the main difference. Okay, let's write a few remarks because this looks somehow complicated. Remarks. First of all, the way that we should be thinking of this is that the mixing time is up to constants m squared n log n plus n squared m to the little o of 1. Okay, that's how we should be thinking of it, so that we don't, you know, worry too much about this e to the something term. Second, let's see why these things make sense. Okay, so first of all, if we look at the super diagonal, these are all the elements right above the main diagonal. Then, and we look at the join process that they perform, A1, A2, all the way to n-1, they perform simple random walk on the hypertorus. So on integers mod m to the n-1. Okay, and we know that the mixing time of this is up to constants m squared n log n discrete time. Okay, so this is why we expect to see this term. This is very well studied. The second thing, why do we get the n squared? Well, let's look at the last column. So bn-1, b1, b2, all the way. So now this process, 1, is a generalized Yeast process. In particular, we know that it takes n squared steps for bn-1 to turn on 0 if we start at the identity. Okay, in expectation. One can make this much more rigorous, of course, but this is where this n squared term comes from. So we expected to see these things. Now, of course, the dependence on m, this m to the little o of 1, could be sharpened. We don't claim that we have the super sharp answer here, but this is the best bound that we have jointly on n and m. And this brings me to the history of the model. Okay, let me write again what we have. So the mixing time is m squared n log n. Actually, let me move this a little bit. Okay. There we go. Plus n squared m to the little 1, just to remember and compare with what I'm about to write. Okay, so the history behind this problem. So first of all, it appeared many years ago in a PhD thesis by Maria Zach, and it became a very good model for Diaconis and Sly of cost, not only to study but also to develop new techniques. So they focused at first in the case n is equal to 3, so the 3 by 3 matrix. In this case, our group coincides with the Heisenberg group, so their papers bear the title something on the Heisenberg group. And they proved that the mixing time is of order, m squared. So they actually produced a series of beautiful papers. And it's not because the outcome would be surprising, but really because they introduced new techniques. So one technique is a growth technique. Another one is using Nash inequalities, and another one uses Harnack inequalities. So this seemed to be a good model to develop new techniques upon. However, these techniques were really bound to n is equal to 3 or n being fixed. So the constants that they got in front of the m squared were actually exponential on n. So that is why they didn't write their bounds in terms of general n by n matrices. I want to write another similar result, although Percy has lots of papers on the case n is equal to 3. It would take 1 page just to write them all down. I do want to write, however, a recent result of his with collaborators. So Dan Bump, Diaconis, Hicks, Miklo, and Widom reproved the case n is equal to 3, but this time they used an L2 bound, and this was important for us. So we used it, and this is why I really want to mention it. Okay, this is the case n is equal fixed, m is growing. Okay, so let's say here n fixed. Now n growing. So first of all, the first bound on n was due to Ellenberg, who provided a bound of order n to the 7th. But this was in 93. But more recently, Peres and Sly, so this is, sorry, the case m is equal to 2. More recently, Peres and Sly found the optimal order for the mixing, which is n squared. Again, for the case m is equal to 2. Okay, so for n growing and m constant, basically we know that the answer is n squared, at least for the case m is equal to 2. And then the joint bounds that are known, well, the one that used to be basically the best one was used to Stong in 95, and his bound was n cubed m squared log m. Okay, so this log m wasn't, I mean, the n cube is not very good too, but the log m was also an extra term. Here I want to add that one more technique that was developed using this model, the n by n upper triangular walk, is due to Arias-Castro, Diaconis and Stanley, who used supercharacter theory to study the L2 mixing. And in 2004, they proved the joint bound of n to the 4th, m to the 4th log n, which is worse than Stong's bound, but the technique was very important because basically this is the only example where we have supercharacter theory, this part of representation theory, giving something really good for probability. And as part of my thesis, I sharpened this technique using supercharacter theory to improve this joint bound to n to the 4th m squared. So this was better in terms of m than Stong's bound, but then to the 4th was worse. Okay, and these are the bounds known for this specific walk, and you can see, you can compare how we got something more precise. I do want to mention a few more things concerning history and references, because features of this walk have been studied, and that and this has been very important. Okay, so features of the random walk, which have been studied, and some of them we are going to crucially use. So first of all, and we don't use this, but it is important, for the case m is equal to 2, as I mentioned earlier, the class column of the matrix performs what is known as the Yeast process, a very important process in chemistry and physics. And in a recent breakthrough, Ganguly, Lubetsky, Martinelli proved cutoff for the Yeast process. And this is really a breakthrough. I mean, we are we are far away from proving cutoff for the n by n matrix talk. I will, when I am done with the talk, I will mention open questions there, but this was really, it's an amazing paper and it's a breakthrough. Now, Ganguly and Martinelli managed to prove cutoff for the k last columns of the walk where k is constant. So not only one column exhibits cutoff, but say three columns will exhibit cutoff if we only look at the last 3 columns. So this is due to Ganguly and Martinelli. And this is more recent. And lastly, and for some reason I forgot to write down the date, but I think it's 2016 or so, Diaconis and Hoff studied the diagonals of this process. So I'm going to write it this way. So if you look at the top corner entry, this is not a 0, this is just circling the corner entry. They said that this mixes in 2 to the n m to the 2 over n minus 1 steps. And this 2 to the n might be disheartening, but in their case, they wrote the paper for fixed n, but tracking down the proof, this is the correct constant in front of it, and it was good enough for Allan and I to do analysis. So this is something that we use. I want to finish off the history concerning this walk by saying that for people who know what cutoff is, it's extremely difficult to get sharp answers for this walk. We don't even claim to have the exact precise order, as I told you earlier. But there have been efforts towards this direction when you consider random generators for this type of group. Jonathan and Sam Thomas have results proving cutoff when you have random generators. And these are really, really important results. They're very difficult too. Okay, so now I want to get into some math. These are all the references I wanted to mention. And for the sketch of the proof that I will provide, I will focus on the case M being prime, so the second theorem. And the only reason why I do this is because the Diaconis-Hoff theorem actually only works for prime M's. Now, both of them have said that it should work for general M, but that's what they could prove. So this is why we restrict to M prime at first. And to motivate, so let's write a sketch of the proof. To motivate what's going to happen, we are going to study the first row of this matrix. Unlike the previous papers, we are going to focus on the first row and the process that it follows. Okay. Okay, so there's a question about the motivation of the problem, and there are many answers. The one that I was selling here was that it was a great model for developing techniques, and the more techniques that were introduced, the more hard this problem became, meaning that these techniques were not sufficient for a good bound. But there's better motivation than what I'm saying, which is that it is a natural generalization of the Yeast process, which is a very important model in physics, and the Heisenberg group in general. So the case n is equal to 3 is very important for physics. Also, this model was studied, so there were many limit type of theorems studied based on this model. So Emmanuel Brouillard's thesis was providing limits for this type of problem, and the intuition behind mixing times and limits sometimes intersects. Anyway, so I'll get back to the sketch of the proof, where I said that I'm focusing on the first row. And the reason why we are going to focus on the first row, so let's call QT the distribution of the first row. Now, this is not a Markov chain, this is a sketchy type of thing. We want to condition on what's happening on the rest of the matrix. So we are going to define FT to be the same algebra generated by the moves that have happened by time t on the n-1 times n-1 box. By that I mean this part of the matrix. This is the n-1 by n-1 box. Okay. Also, FT will also include the information when the clock of the second row will ring, and the times that the second row clock rings. This is why it was good to put everything together, because here we forget what the signs are. So we don't know when the second row clock rings, we don't know if we're adding or if we are subtracting when we condition on FT. This is the randomness. Okay, so QT actually will be the distribution of the first row given FT. Okay, and the first lemma that we want to write is similar in flavor to a lemma that appeared in Peres and Sly, which said that the total variation distance is lesser for the n by n matrices is less or equal than the total variation distance for the n-1 matrices plus the expected total variation distance between QT and the uniform measure on the first row. So this is uniform on first row. Okay, I'm going to explain this in a second, but basically this says that if we manage to study this quantity, then we do induction. And we can get our bound. And this is basically the main first idea of the proof, to do induction. And this is why studying the first row at the mixing time suffices. Okay, just very quickly, very quick explanation on why this is true. Or sketch of the proof here again. Basically, we can couple the n-1 box with a random, a uniformly random n-1 upper diagonal matrix, but with probability dn minus t. So we can couple xn minus 1 t, so this notation just means that this is the n-1 by n-1 box with a uniform element of gn-1m, but with probability dn minus 1t. So this is how we explain this term. This coupling can be done FT measurable. And so now conditional on FT, we can couple the first row, but with probability qt minus pi, the total variation distance. And then we average to get the second term. We take expectations. Okay, so anyway, this is, as I said, very similar in flavor to a lemma that appeared in Peres and Sly. And the goal from now on will be to focus on this term, because as I said, we will be moving inductively. Okay, so to motivate the definitions to come, to study, oops, sorry about that. Again, I want to indicate that this was QT. To study QT, we're going to do a spectral bound. And the point is that at the times that the second row clock rings, we are either adding the second row or subtracting it. And this really looks like a random walk on the cycle. So let's call S1, S2, SK, little k. These are the times that the second row clock rings. And so remember X SI2, this is the configuration of this second row at time SI. Okay, if we have this information and we are conditioning on FT, so basically we we can use this information, we will have this quantity appearing. So, okay, this is discrete time. This is discrete time, but I'm going to write it in continuous time in a moment. So this quantity will be appearing in the eigenvalues. Can explain in a second. So this quantity will be appearing in the eigenvalues of Qt. What is Y? Y is a vector with n-1 coordinates. Why n-1? Because these are the coordinates that are non-zero in the second row. And for every Y, we are going to have one eigenvalue contributed for Qt. Okay, as I said, we're going to do an L2 bound. And this quantity will be important for the eigenvalues. So because of this, we are going to define, and everything will be explained again in a moment, ZY2 T to be this inner product that I wrote up there. So this is the inner product of a vector Y with the second row. And we want to count, we hope, so as I said, this will be crucial for the eigenvalues, and we want the eigenvalues to be small, as I will explain later. For them to be small, we hope that this inner product defined is big most of the time. And so I'm just trying to motivate the definitions to come. So we're going to count for each Y, we're going to count how many times this inner product is big before T and M, which is the mixing time. So number of times that this thing is bigger than M/8, for example, inside the interval 0 TNM. Okay, and we hope that this actually happens most of the time. So we will define the following event, which says that this quantity is bigger than, say, 1/3 of TNM for all Y, but not whatever is generated by this coordinate, because this coordinate is always equal to 1. Anyway, this is a technicality that doesn't need to be explained right now. Why is this important, this event? So our main lemma to proving our main theorem says that, hey, we wanted to study this expectation, which was the expected total variation distance between the distribution of the first row and the stationary measure of the first row. So if we condition on this, so if we assume this good event that, you know, this entry is really big, then this expected distance is very small. So we get the bound that we want. So here C will be bigger than 1. Okay, so this is a nice event. Like if this quantity is big, it gives us immediately the bound that we need to produce our main theorem. And the good thing about this event is that it happens with high probability. So the complement has very small probability. B is a constant here. And it decays in this following way in terms of M and N, which is good for our bounds. Now remember, the main theorem was proven using induction. So it is important that we have something summable on N here. This contributed to the window to make sure that we have something summable on N. And similarly here, this is also important that is summable on N, and it ends up with giving something that goes to 0. Okay, so so this is, as I said, the main tool. Now I am going to duplicate this. Give me a moment. So I am going to change pages and move this up in case we want to still look at it. Oh, it hasn't updated the information. That's okay. It's fine. My computer didn't synchronize things. That's okay. So let's now define the eigenvalues properly. I just roughly told you what they would be, and I want to do it in continuous time. So again, QT is the distribution given that sigma algebra. And so in continuous time, we are going to have the following quantity, which comes basically from simple random walk on the cycle, basically. And the L2 bound that we have, so we wanted to bound this thing. So the L2 bound, the famous L2 bound, says that this is going to be less or equal than, we sum over all these y's that I told you that are vectors on n-1 coordinates, e to the minus 2. I'm going to write it down and then explain it to you. So here, remember S1, S2, all the way to SK are the times that the second clock rings, second row clock rings. And we are keeping track of the corresponding lambda YSI, and it appears as a summand up here. So this is a standard eigenvalue, eigenvector type of argument that is used to bound the L2 norm. Okay, and so the point is that we want these eigenvalues to be small enough, and that's why we wanted this inner product that I defined earlier to be big. Okay, and so here, now we have assumed that this inner products are big enough because we said that we are on this nice event where these inner products are indeed big. And so we can consider separately E1, which was a problematic case. And in fact, it turns into something very nice, but no need to write it down. And all the other terms that are not in the span of this vector, well, instead of this quantity here, we could plug in m/8. This is what this definition of e to the TNM said. So we can write e to the -2 k minus k times a constant, which is cosine of pi over 4. So square root of 2 divided by 2. So it's a very specific type of thing that we get here. So all I'm trying to say is that this is something that is very controllable because it corresponds to the random walk that this entry performs, the 1-2 entry performs. This is random walk on the cycle. We know everything about it. So this first summand causes no trouble. This second summand is how many such vectors do we have? Well, we have m to the n such vectors of this thing. This is not a cosine anymore. So k is the number of times that the second row clock rings, which is roughly the mixing time, and the mixing time is such so that this is killed. So we don't have any issues here. Okay, but this is all based on the fact that we assume that this event happens, this beautiful event happens where these entries are very big. And so now we have this final last question. Why is this entry big? So let's look at this thing. So we have y to be a vector on n-1. And if you're lost with the previous computations, we can come back now. It's going to be a little bit different. So we have xt to be our matrix at time t. And so what we do now in order to produce this inner product is that we create the column process zy at t, which is we take the inner product of y with xt. So this is a column process. So this is z1, z2, zn. In particular, for example, this last thing is the last coordinate of y. That's what the inner product would be. And this column process follows, again, the same dynamics as our Markov process, which means that, you pick a coordinate and you either add it or subtract it from the coordinate above. And all we want is this, this entry to be big most of the time. That's what we want. And Diaconis and Hoff can help us with that because they said that, look, they said how long it takes for this to become random, uniformly at random. They said it takes 2 to the n, okay, minus 1, 2 over n minus 2. Okay, and as I said, we found a way to manipulate the constant here. Maybe I shouldn't get into these specific details, but all I want to say is that Diaconis and Hoff told us that ZYT2 will be big. And we had to do a little bit extra to add the for most of the time part. This little extra, just because I don't want to lie too much here at this point, I will say that this is where we did not play with a second coordinate. Instead, we played with the I coordinate, which was square root of log m. So we proved that this coordinate, this ZYT, is big. And somehow this ensured that the second coordinate will be big. This is a non-trivial arrow over here. But at least I want to not lie too much. So if we plug this into here, this is where this e to the square root log m came from. Okay, and it is still m to the little o of 1. And to study, this, whether this is big most of the time, because this is how we induced this problem to this problem. What we did is that we took the time interval, 0t and m, and we cut it in sub-intervals of length L, which is exactly what Diaconis and Hoff said it should be. And so we said that, look, if this much time passes, the Diaconis and Hoff say that in the next interval, this entry should be big. Okay, so meaning that a specific time in the next interval, so this time has a very good chance of having this entry being big. And then we sum the indicators of all the times where this entry is very big, and we do a Markov, we can have a bound for its expectation. It has a decent expectation, and then we do a Markov inequality type of argument. So these intervals where we have the good property that this entry is big are good intervals. And so the last thing that we had to ensure was that indeed we had enough good intervals, which has to do with this arrow over here. So somehow, not only we wanted this to be big, in fact, we wanted it to be non-zero, for example, and we wanted to make sure that it is non-zero for most of the time. To do this, and this is the very last thing that I will explain, because I know these are way too many ideas. So again, we look at this process, and we want to, the column process, which was the inner product between Y and each row of the matrix. So to look at a specific coordinate, for how long this is non-zero, well, there are two main key ideas that are quite simple, actually. One is to follow in this random walk, which has the same dynamics as the initial process. We follow the coordinate that, the first coordinate that is not zero. And the good thing about this coordinate is that it performs Bayes' random walk. So it moves at rate 1 to the next coordinate, while it goes back with at most rate 1/2. So we know that if at some point this coordinate zy is 0, and say this is the top of our interval, soon this star will come back to it. In fact, in constant continuous time, this star will come back to it. So this is one main idea. And the other thing is that if it is non-zero, so if this I coordinate is not 0, then it will remain non-zero for at least a constant time, continuous time, because the only way for it to turn non-zero is to have the previous coordinate added to it. Combining these two ideas, putting them together, we do get that the ith coordinate is not 0 for most of the time. And then Diaconis and Hoff will help us get that this will imply that the second coordinate will actually be big. Okay, so this is the important arrow that I was trying to indicate earlier, but I didn't say very clearly. So in the very last minute, I want to just say, okay, I think I have convinced you that this is a complicated argument, and we are very far from discussing cutoff, meaning very far from examining what M and N should be so that the mixing time has a very sharp threshold. So some open questions that are maybe more doable than asking cutoff for the general N by N case. Open questions are one, for general M, can we study, say, cutoff for the last column? You know, generalizing the breakthrough result of Ganguly, Lubetsky, Martinelli. Okay, of course, a natural thing would be to try to improve the bound that Allan and I proved, but also in terms of the lower bound. The lower bound, the way that I showed it to you, doesn't tell us, you know, what should be the M term next to the N squared. I just told you there is an N term, so it might be a good idea to try and see what the correct dependence next to the N squared is. And finally, for the case M is equal to 2, if one has to ask about cutoff for the matrix block, the case M is equal to 2 sounds much more trackable than general M. In fact, you know, if M is, I don't believe there will be cutoff for every M, but for M is equal to 2, one could try to look into cutoff. And this is the point where I want to say that Ganguly and Martinelli in their paper say that they have some simulations saying that the last column does not keep track of where cutoff occurs. So remember the mixing time in this case, the M is equal to 2 cases N squared. So one could think that the last column has all the information, but they say that's not true. And so given these open questions, I think I'll stop here. Thank you for your attention.
Thank you, Evita. Let us all mute our mics and thank her.
Thank you.
And I think I will stop the recording and we can have an informal discussion at this time.
Yes.